So, life expectancy in the United States varies a bit from state to state. The lowest life expectancy at birth in 2012 was 73.09 years, and that was in the District of Columbia. Interesting, especially as we'll see a little bit later on that there is a interesting fact about DC for a particular population, but we'll get to that. The highest, 80.23 years, was in Hawaii. Must have to do with less stress. I don't know. Or less variations in temperature. Maybe if you don't have wide temperature swings, humans do better in the long run. You know, if they're not sweating to death in the summer and they're not freezing to death in the winter, maybe that's easier on the body in the long term. I don't know. The mean of all life expectancies is 77.19 with a standard deviation of 1.57 years. So let's calculate the z-score for Washington, D.C. So the z-score would be, in Washington, D.C., the life expectancy was 73.09 minus the mean, which was 77.19. And then we're going to divide by the standard deviation, which is 1.57. And I imagine several of you have done that already. What does that come out to be? Negative 1.66. Oh, there seems to be some disagreement.
I got 2.611, yeah.
Fight. Yeah, I think it's more than one. Yeah, it's negative 2.61. All right, so interpret this z-store in context. So the life expectancies at birth for people born in the District of Columbia in 2012 was 2.61 standard deviations below the mean of all people born in the U.S. in 2012. Now, before we go on, a question for you. Can I use that z-score to find what percentile they are in? I love waiting long enough after you ask a question and people answer. People will start to change their answer, and then they'll change it back if you wait long enough. The answer is no. Why not?
Don't have enough context. Well,
We have plenty of context.
Because you just
Nope.
the mean of standard deviation.
well, we have. Don't we
Well,
have it? You know, actually, I'm confused why we can.
Just because we know the mean and the standard deviation
Oh, right.
doesn't mean that this is a normal model.
Yes, Mr.
Oh, you guys make me smile. Yeah, nowhere did it say that this is unimodal and symmetric. We don't know that. And so we can't just assume that it is. Okay, in some cases, you'll know enough to know that it can't be. So, for example, if I gave you one where I said, you have this set of data about whatever, and let's say that I know that the mean is 50 and the standard deviation is 30. How do I know that cannot be a normal model?
Because a lot of the data we call like way far from the mean.
Big standard.
I need to be a bit more specific than that.
Like the standard deviations 30, mean is 50.
Yeah.
Like
Yes.
Because isn't it like if you go 2 standard deviations above that, like okay, the mean isn't realistic for like its whole range, right? Because you'd have
Nope, that's not the problem.
way far.
see, at least I wasn't just wrong.
Like because wasn't this one of the problems? Like the standard. Whoa, wait. Like, if you go 2 above and 2 below, right, or something like that, like it's still not gonna have all the data in there.
How do you know it's not going to have all the data in there?
Or it's just like a sparse range.
Okay, so let's think about this. If the mean is 50, right? And I guess I should have told you one more thing in context. Let's assume this is something that cannot be negative. If the standard deviation was 30, 2 standard deviations to the left is already into negative territory.
That's what I said basically.
It's basically what getting there.
It may have been what you were thinking, but it's not what you said. Yeah, if you go 2 standard deviations, we expect there to be some data in here. The normal model would expect 2.5% of your data to be out here, and there's nothing. This is more likely to be something that, was like this, where this is 50 somewhere in here, where because of the skew, it's pulling the mean upwards from the median. Okay? All right. So, Connecticut has a z-score of 109. Okie dokie. Interpret this z-score in context. So, basically, we're going to write exactly what we wrote up here, except it's going to be 1.09, and it's going to be Connecticut instead of the District of Columbia. It's the same question. Life expectancies at birth. For people born in Connecticut, Connecticut's a weird word. in 2012 was 1.09 standard deviations, above the mean. Then it says calculate the life expectancy at birth for, this really doesn't make any sense when you read it. Everyone reads into it. It should say for people born in Connecticut in the year 2012, not for Connecticut. Connecticut doesn't have a life expectancy.
I mean, like, we'll probably figure out.
200 and however many years old.
Yeah.
250.
So
That's
there are actually multiple problems with this. That's just the first one. The second one is, if we're going to use the z-score, what are we, to try and figure out what the life expectancy is, what are we assuming? A normal model. Okay? So let's fix this for people born in Connecticut in 2012 if the life expectancies have a distribution that is nearly normal.
Why does it need to be a normal distribution for us to use the z-score to calculate it?
Because what we're about to do is we're about to pull up on our calculator a normal model, put in that it's 1.09 standard deviations.
Oh, because it uses a normal model to figure out what the. Well, it already told us what the standard deviation was.
Right. So let's do this. Oops. So for the US, 77.19, 1.57. So 77.19. Was it 1.57?
Yes.
Thank you. So we're going to use a normal model.
Okay.
And it's 1.9 standard deviations above. So actually, I don't need my calculator to do that. I just need to do the mean plus 1.09 times the standard deviation. But I'm assuming that this is a normal model. Okay, does that make sense?
Yes.
So it would be the mean 77.19 plus I'm 1.09 standard deviations above. The standard deviation was 1.57. Whatever the heck that turns out to be. Yes.
Oh, sorry. She has the answer.
Oh.
I was gonna ask why. This might be dumb.
It's okay.
Why we couldn't just add 77.19 plus 1.09? Why we had to multiply by the standard deviation?
1.09 tells you how many, that's standard deviations. This is in years.
Yes.
Z-score has no units.
Oh, because we have to figure out how many what actual difference that makes.
Right,
Okay.
right. And I'm sorry, someone had it? 78 point what? 90. Okay. So if we go back to this and we put in 78.90, we get that's about 86.2%. And you're like, well, how do I know that that's the right number of standard deviations? All right, remember 86.2%. I'm going to go back and make this and it was 86 point what? 2, thank you. Look at that, 1.09 standard deviations. Okay. All right, moving on. So life expectancy also varies by race. Blacks in the United States tend to have shorter lifespans than whites. The mean of the state average life expectancies at birth for whites, that is a long thing to say, is 77.96 years, and the standard deviation is 1.29 years. For blacks, the mean is 72.33 years with a standard deviation of 1.46 years. All right, so we have now two different sets of data. The state with the longest life expectancy for blacks is Massachusetts at 76.36 years. For whites, the longest life expectancy is in the District of Columbia at 81.54 years. Now, before we go on, and this is real data, go back up here. The lowest life expectancy was 73.09, and notice the blacks have a very low life expectancy. It's 72.33. It's less than the overall. Well, why is that? Well, because they're not all black, they're not all white. There's probably quite a mix, but there's enough to where that's bringing it down. The causes for that, we're not even close to getting into that yet. We'll get to causality a little bit later. Just know at this point, just because two things are correlated together doesn't mean that one caused the other. And I'll give you a quick example of that. In elementary school, shoe size and reading level are strongly correlated. And actually, I should say the right word. Most people would say that. The correct word is strongly associated. Correlation actually means something else that we'll get to. They're strongly associated. Why is that? Because kids with bigger feet tend to be older, and so they're at a higher reading level. But if you just look at the data, you're like, oh, people with bigger feet are smarter. No, you can't make that kind of logical leap. All right, so which of these life expectancies is more extreme for the populations? So let's look for black. I'm going to underline this for black. So what I'm going to do is find the z-score for each of them and see which one is more extreme. So in Massachusetts, my z-score is going to be 76.36 minus 72.33 divided by the standard deviation divided by 1.46. 2.76. So those are blacks in Massachusetts. And then for whites, the longest life expectancy and isn't that interesting? For whites, the longest life expectancy is in DC, where overall that's the shortest life expectancy. Why is that?
All the old white politicians though.
Probably.
Yes.
Although this is people born there theoretically. But, okay, so extend your idea of one generation. Who are the white kids that are born in Washington, D.C.? It's the children of the old white politicians who tend to have more money, better health care, I mean, there's a zillion things you can point to. All right, so the z-score there is 81.54 minus 77.96 over 1.29. 2.78. So ever so slightly, the whites in DC. By the way, I don't need to know that my data is nearly normal to do this. I'm just comparing z-scores. It doesn't have to be normal data to compare the z-scores. Okay? Now, because it is telling you how many standard deviations it is above, I would be leery of doing something where I was comparing one of them is above and one of them is below. Because if it's not nearly normal, then you're like, okay, that may not be a good ruler anymore. All right, so Connecticut has a z-score. Again, with Connecticut and the z-score, we'll assume what we assumed before is that we're talking about people in Connecticut and not the state itself. Right, Bronson? Oh, he is out.
Bronson! Oh, wow. What's happening?
Wait, you should do something funny.
No, it's Bronson.
You okay?
That's how we solved a cure for cancer.
Yes, go Mr. Davis! Everyone give it up. Give it up, guys. We're all like clapping because you're making all this. You're still not. Wow, that's crazy. That's crazy.
All right. So we'll also assume that this is a normal population. So in Connecticut, we have the z-score for life expectancies for blacks was 1.07. So what can we do? Well, we can say the z-score is equal to, I'll call it the life expectancy minus, for blacks, the mean was 72.33.
Yes.
And the standard deviation was 1.46. So again, this is assuming that we have normal or nearly normal data. So we can solve this, and you can actually, do the solving. It's not hard mathematically. You just multiply by 1.46 and then add 72.33. But let me show you that in another place where the NumWorks is pretty cool. You can type in that equation. If someone would read that equation to me, what was the left side? 1.70. I always have to, I'm not as used to this one yet. Where is the equals? Oh, it's shift pi. Equals, I'm going to put parentheses so I can get my numerator. You can call it whatever you want. The easiest variable is just up here is x minus, what is it? 72.33 divided by 1.46. Thank you. And you just go down here and say, solve me that equation. And it's 74.812. There is a solver on the TI. I don't like it. It's not as bad as the, because we were trying to do the drawing of the normal model, which was fairly horrible. Let me see. I'm trying to even remember where it is. Nope, it's not there. That's the other part, is they tend to hide things on the TI, and I'm like, where is it? I'm sorry? Yeah, there's a solve button, but you have to put it into something first. Yeah, I don't remember. There is a solver.
It's a numeric solver.
It is
So press math.
Yeah.
And go up one.
Go up one? Oh, so down to the bottom.
Oh yeah.
I don't know that that's it. Okay. You have to put in,
The equation.
you put in the left side into one of those boxes,
Yeah.
and then you put the right side into the other box.
Then you graph
It graphs it?
it. No. You press graph and it will solve it.
Oh, okay. Because graph is where it says okay,
Oh yeah.
and it gives you x is 130. I must have typed something wrong. Oh, and then you have to press solve after that.
Yeah. Complicated.
Oh, the 130 is your guess.
Yeah. I don't know what's the 130.
Yeah, I don't know where that comes from. But then you get the 74.82 that we got here. Now, frankly, you should be able to solve this equation without any calculator, or at least, any fancy thing on a calculator. All right, and then for whites, it's 1.09 is equal to the life expectancy minus 77.96 divided by the standard deviation, which is 1.29. So again, I would just do 1.09 times 1.22 or 1.29, and then I would add the 77.96. What is it? 79.37. And I just realized I never wrote down the life expectancy for this one.
74.812.
0.812.
You mean 812. It's not 820.
Devin Jackson, yes.
Yeah, you're right.
All right, let's leave that last bit. Let's go ahead and quiz.